Okay, so for this next lesson here, I know on the video you guys won't see this if you watch this, but I want to go back to this voltage machine in front of us here. Okay. So where did I leave off? There, you've got a negative end right here, a positive end right here, and we're shooting electrons as fast as we can, basically through this system right here. Okay. But we're trying to figure out, as a model of the atom, if I were to maybe draw a nicer one right here, imagine that you have a nucleus here. Nucleus. Boy, I can't write today. And there's electrons orbiting this nucleus. What could some of the electrons do as they go basically flying through here? Some of the electrons could hit a nucleus, but sometimes those electrons might hit other electrons. Right? So as these electrons go flying through this tube here, as we're accelerating them due to voltage, with Rutherford's model, he kind of figured, well, if the electrons are outside of the nucleus, what if an electron hits another electron? Okay? And haven't we kind of talked about that a little bit with the idea of things like Compton scattering? I know that was a wave hitting an electron. Well, that's basically what we're seeing right here, is an electron hit another electron, and it caused it to move. And then later, that electron came back to where it was supposed to be, and it emitted light. And that's really what's happening in all of our lights here, is that electrons are changing what we call energy levels. And that's what I want to show you in Bohr's slides in a little bit here. Energy levels are changing. As electrons get hit, they go from here to here, and they upgrade their energy levels. But then they drop back down, and in doing so, they lose the energy they've gained in the color of a certain frequency of light. Okay? And that was Bohr's revelation. So why don't I actually start by playing this YouTube video that's on my first slide, and let me walk through my slides in order, because I feel like I'm getting out of order here today. I'm scattered right now. Let me get back on track. Let's start with this YouTube video.
We might say the atomic age started with the work of John Dalton. Dalton proposed the atomic theory in 1803. This picture of the world where everything is composed of atoms helped explain what had been observed in chemical reactions. For instance, different elements always combined to form chemical compounds in amounts that were simple whole number ratios. Dalton proposed that each element had its own unique type of atom with a certain characteristic weight. These atoms were very small solid particles that were indivisible. That was the model of the atom for almost 100 years. Since Dalton's first conception, the model of the atom has evolved over time. Each time new experimental observations were gathered that couldn't be explained by the atomic model of the day, the model had to be revised and refined. For instance, the discovery of subatomic particles meant Dalton's model that said atoms were indivisible needed some work. In 1897, J.J. Thomson was the first to discover a subatomic particle, the electron, through his experiments with cathode rays. At this time, people weren't sure if cathode rays were waves or particles. Thomson was using magnets and electrically charged plates to deflect cathode rays and thereby estimate their mass. He showed that cathode rays must be made up of negatively charged particles that were over 1,000 times lighter than the smallest atom. That's hydrogen. Before this experimental result, it was thought that the smallest particle was the hydrogen atom. To account for his observations, Thomson proposed the plum pudding model of the atom. If you've never had plum pudding, that name may not make a lot of sense to you. So imagine you have a dense, chewy cake with little raisins all through it, maybe like a raisin bagel, or a chocolate chip muffin if you prefer. The cake part is the bulk of the atom, and it's positively charged, while the little sweet bits of raisin, or chocolate, would be the negatively charged electrons. The Thomson model stood for about a decade, until the work of Ernest Rutherford. Rutherford and colleagues, in an experiment performed in 1909, found that a beam of alpha particles, that's a kind of positively charged radiation, shot at a target of very thin gold foil, mostly passed straight through to a detector behind the foil. But occasionally, a particle would be violently deflected back, as if it had hit something massive. As Rutherford said, it was quite the most incredible event that has ever happened to me in my life. to hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute massive center carrying a charge. The result implies that an atom must be made mostly of empty space, but with a small core of positively charged material.
Okay, let me pause there for a sec just to make sure this is clear. So this was the previous model. So this was Thomson's model, right? And it kind of made sense that particles would phase right through it because really these electrons right here, they're not really going to get in the way all that much, right? And so maybe there'd be a little bit of deflection, but I mean, they didn't even fully know what electrons were at this point, right? So they expected this, but this is what happened instead, the stuff that's kind of hidden under the typing on top, right? Where once in a while a particle would hit the nucleus, right? So was Rutherford right? Yeah, we believe there's a nucleus. But the next part of this is going to explain why he had to figure out the electrons yet.
Most of the mass of the atom. This was the nucleus. Again, the atomic model had to be updated to take this new information into account. There was a problem almost immediately seen with Rutherford's model, however. If the electrons are out in this empty space around the positively charged nucleus, what is keeping them from just giving in to the electrostatic attraction towards the nucleus? Why doesn't the atom just collapse on itself from all that attraction?
Why would it collapse on itself? Well, if it is actually going in like an orbit, like he kind of suggested, if electrons are going in orbit, they're accelerating, right? I mean, they're accelerating centripetally. Right? Well, we've learned that anything that has centripetal acceleration gives off electromagnetic radiation, right? Anything that has any charged particle that is accelerating, it gives off EMR. Right? So therefore, one of the slides I showed you, what was it, right about here, this is what they expected should happen then. Right? They would expect that this particle going around in a circle would lose an X-ray, and then lose a UV ray, and then lose a gamma ray, and then lose some infrared light. That's what they expected should happen, and eventually the negative electron should hit the positive nucleus. Doesn't that actually make logical sense? Don't positives and negatives want to attract each other? And so that's where Rutherford's problem was. I'll let the video keep playing, is that he knew his model couldn't be right because logic would dictate that all matter would collapse on itself. And clearly it doesn't.
Niels Bohr, who did postdoctoral work in Rutherford's lab, came up with an elegant solution to the collapsing atom problem. In a publication in 1913, Bohr suggested that the negatively charged electrons are found in concentric circular orbits around the positively charged nucleus, much like how the planets orbit the sun. We sometimes refer to the Bohr model as the planetary model.
That's wrong, actually.
According
We don't usually refer to that as a planetary model.
electrons are found at fixed energy levels, orbiting at fixed distances from the nucleus. The path closest to the nucleus has the lowest energy level, and the energy is generally higher the farther the orbits are from the nucleus.
Okay. So I found this YouTube video online, and I don't love every bit of it because we don't usually refer to Bohr's model as a planetary model. It's usually considered to be the Bohr model. Here was his big difference. He suggested that maybe electrons, maybe they still go around in circles, but he theorized maybe they don't necessarily orbit. They don't go in circles like planets do. Maybe what they do is they only go in certain rings. It can either exist in this ring, or this ring, or this ring, or this ring, and that's the only place it can possibly be. And what can happen is these electrons, they can jump from ring to ring. And literally, he was suggesting the first idea of teleportation. Because his theory was you'd never find an electron, you know where my mouse cursor is right here between them? He suggested you'd never find an electron there. It can't possibly exist there. It either exists on this ring, or it exists on this ring, and if it has to move from one to the other, it instantly goes there. It's never like moving in between. As an example, if I had to go from here to the door, and you were to I'd say, close your eyes, and then I go walk from here to the door, and then I say, open your eyes again, you would logically infer that at some point I was halfway in between. That's what Bohr was suggesting is not the case. He was suggesting they literally traveled from orbit to orbit, which was a problematic word because they were still working on the idea of like planets orbiting around, but it was a different concept. It was more the idea of like hopping from one stage to the next. Okay. I'm going to pause the video now because it's actually accomplished what I wanted to, which was a little bit of review, and I want to go into my notes. So here's our context again. Rutherford was working, he worked with Niels Bohr, and Bohr tried to combine the planetary model with quantum models, and he basically suggested that there was only certain energy frequencies. And he actually had some support for this. So I want to go back to this device up here at the beginning. Okay. I need you guys to come kind of gather around here, honestly, because this doesn't work from your desk. So like, come be mobile, come stand around here, and grab one of these devices called a spectroscope. Okay, so I'll pass them out here. And then I'm going to turn this thing on in 30-second increments. Okay. Once you grab your spectroscope, what you need to do basically is aim it at some sort of light source. And it functions like a prism. There's lots here. We still got more. Did everybody get one? Okay. So like take this thing and aim it at the light. And off to the side, you should hopefully see some bands of color. Currently, I'm looking at the light there, and I've seen like a green and a red band, like off on the right-hand side there. Yeah, well, aim it right at the light. Aim it right at the light. I see a purple, a teal, a green, an orange, and a red stripe. Can you guys see that as well? Aim it like right at that light. Make sure the little slit that you're looking through is right at the light there, and you should see a purple, teal, green, orange, and red. Can you guys see those bands of light? Do you want one to try here? Were you able to see that? Okay. I'm going to turn this guy on right now. I want to try the same thing here. Look at this. Now, you might need to come closer, look one at a time, but aim it directly at the light here. I'm going to turn it sideways, actually. And I'm looking for the same thing. I'm looking for little bands of light in the corner. Okay. Here's what you're looking for, by the way. You're looking for a picture that looks something like this top line here, where you get these vertical bands of different colors. Okay. Try either getting that by looking at the light or by looking at the xenon here. Okay. It's one of those things where I won't be able to do it for you, so you're going to have to kind of like test it out. Well, okay, so there's like a little slit of light that you're seeing there. Make sure that that is focused directly at the light from there. All right. And then try to look for some color bands. You know there's like a 4, 5, 6, and 7? Okay, right below that, underneath that, there should be some color. That might be it. Yeah, you might only get a couple of colors here. I see a purple.
Oh, I see tires.
Yeah, I see most of the rainbow there, actually. Okay. Let's turn that off and try the other one for a second here. Let's try the other one now. Try Krypton.
Wow, that one's cool.
Okay, for this one here, I see about 2 purple bands, a green and an orange.
Yeah.
Depends exactly on where you hit it, but I'm seeing 2 purple, teal, and orange. You see that too? If you haven't had a chance to try this, come give this a try, because experience is kind of the point here. Krypton, I'm seeing 2 purple bands, a teal, and a yellow. I almost wish you could like take a picture of it like that almost. I wonder if I could do this. Is that going to work? Oh, here we go. Hang on.
Yeah, that's what I was gonna do.
Yeah.
An orange, a purple, and a green.
Oh, this is tricky to make work, though.
It works, I think, kind of.
Okay, we're going to get this to work here. I got to turn the flash off. Where's the flash here? Yeah.
Is that warm?
It's going to become soon. Here, we better turn it off for a second here. We'll give it a rest for a second. I'll try one more time. I'm not going to try it. It's high voltage and I put fingers in sockets. Okay. Well, hopefully you guys were able to see an emission spectrum here, because I want to get back to my notes here. Okay. So here's what Niels Bohr was playing with. He was playing with voltage passed through gas. And what he discovered, guys, can I get your attention back, please? What he discovered is he was able to see patterns that looked like this. And hopefully you guys were able to see a pattern that looked like this. Okay. If you weren't, we're going to try this again on Friday, and I want to spend a whole day doing an activity with emission spectrums. But he saw patterns that looked like this, and it made very little sense at first because he couldn't figure out why you only got like a little red line or a little yellow line and only little bits of them, right? Until he put all of this together and realized that maybe what was happening, where's a good picture of a Bohr spectrum? I guess I'm going to have to draw one. He figured that what was happening is that electrons that normally would circle the nucleus, they weren't actually orbiting. Electrons either were in this orbit here, or they were in this orbit here, or they were in this orbit here. And here's what was happening. Energy from the voltage, because this thing is high voltage, right? What's happening is an electron is being flung with a high amount of voltage towards this thing right here. And maybe this electron would hit this electron right here. So an electron would collide with another electron, and in a perfectly elastic collision, all of the energy from the electron that's being accelerated, it would hit this electron right here. And it would cause this electron to teleport, such cool stuff, literally from this energy level up to this energy level. And we numbered them. This would have been like 1, this would be 2, this would be 3. And so electron from energy level 1 would get hit by another electron and teleport to level 2. Yeah. The electron that's moving to be in between energy levels? Right. Well, that one's really not part of the atom, though, right? It wasn't possessed by the atom in the same way. No, we're still working on ideas like that. Yeah, that things can't exist in all places. I don't fully understand. Why can't an electron do that? Okay, because I guess the space that we're talking traveling, like this right here is a really zoomed in picture, if that makes sense. So whereas like as it's traveling through space, it's still matter that's I guess traveling in a straight line. I don't know that I fully get your question. Can we talk later maybe? Oh, yeah. This electron here. Let me color code them. This electron right here is going to jump from here to here and will not be found right here. Yeah. Okay, hey guys, can you still listen, please? Go ahead. Yeah. Okay, yeah, so this electron is still able to travel through that space here, but as soon as it hits the electron right here, this electron does not keep traveling through there. The second electron just goes from right here to right here. That was the suggestion. Okay, because this electron here was part of the atom, okay? And this electron here is one that you're shooting at it. Yeah, that's kind of the suggestion, yeah. Okay, now I want to finish the story here because I still haven't finished the concept here. Why is there light? So here's what happens. This electron that gets hit, it gets hit with kinetic energy. Kinetic energy of an electron was causing another electron to basically getting bumped to a new ring, okay? But it wouldn't stay there. This electron is like in the wrong location. Keep in mind, this electron is still supposed to be part of a larger atom, right? And so even though the electron is now in the wrong space, it's eventually going to come back to its location, and it's going to lose that energy that it had previously gained. And when it loses that energy, we've now learned that energy is related to frequency, or it's related to a wavelength. And that returning was actually releasing light. That's what he suggested. Let me try drawing this one more time. So sometimes draw is we draw them like this. We're like, this is energy level number 1. This is energy level number 2. This is energy level number 3. And maybe you guys have done some chemistry. You know, like the first energy level in chemistry has 2 electrons. You ever heard this before? The second energy level in chemistry has 8 electrons. The next energy level also has 8 electrons. Anyone ever seen that before in chemistry? Okay. So what they're basically suggesting is there's an electron here in the first energy level. And another electron comes through and rockets through and hits this electron right here. And it could have just kept going right through. That's possible. Could have phased right through everything and nothing happened, right? But maybe it happened to hit this electron and it came through with kinetic energy because we accelerated it using a high voltage, right? Well, then this electron jumped literally from here to here. It teleported from one to the other, which is like such a weird concept because you're like, well, why didn't it actually move along the way there? That's what you'd think it would do, right? But that was his outside the box question. Well, now the electron's in the wrong spot. And so eventually it returns to what we call its ground state. It falls back down again. And in doing so, it lets go of the energy it absorbed. It lets go of the energy it absorbed. Where did it get its energy from in the first place? The kinetic energy of the first electron hitting it, right? So it lets go of the energy it absorbed, and that energy comes off in the form of a wavelength according to the equation E equals hc over wavelength. Let me just finish this thought and then I'll answer your questions, okay? Because I'm not finishing the whole picture here. What that then suggested is it explained why there were these colors right here. Because what was happening is an electron was going from like ground level 1 to ground level 2. And then as it fell from 2 back to 1, it was giving off red light. And an electron was going from 1 to 3. And as it went from 3 back to 1, it gave off this light. And other electrons were going from 1 to 4. Right? Why is it going from 1 to 4? It got hit. But then as it goes back to where it came from, it re-emits light, now in the form of green. And it kind of explains this weird pattern as to why there were only just different sections of light coming off. And that basically became the reason why Bohr suggested his new model. Okay, go ahead with your questions now. That's kind of the theory. Yeah. Yep, still teleporting, yeah. That was his suggestion, is that electrons, they don't behave like matter does, where, you know, like I walk to the door and I walk back. He was suggesting that it either exists here or it exists there. There is no middle, was Bohr's theory, which is like outside the box thinking for 1909, right? Yeah. Yeah. Yeah, I'm not actually sure that he had a theory for what happened to the first electron there, right? I mean, yeah, the first one comes and pounces that guy, right? And then this guy right here, he's still not really part of the atom, so he's, I don't know, he's gonna find somewhere else to get picked up. A proton will merge with it somehow. I'm not actually sure. Yeah, that's a good question. I need to look into that more. So this theory right here then, basically it suggested, again, that energy was quantized and not continuous. Because it meant that really only certain energy levels were possible. You can have the electron in energy level 1, or in level 2, or in level 3, but there is no level 2.5. So the electrons that live inside the atom, you will never find one sitting here in the middle. That was his theory. You can see why this was really strange. I mean, even right now in 2018, this is starting to get towards that quantum stuff where it doesn't really make sense why it behaves this way, because the rest of the world doesn't work this way. Why would an electron behave this way? So, I need to point a few things out. We're going to do this on Friday. We're going to apply a voltage to a gas sample. Okay. And really what that voltage is doing is it's causing electrons to gain some energy, and the energy, they bump up and come back down again. Have any of you guys taken Chem 20? Did you do flame tests in Chem 20? Okay, we're going to do a flame test as well, and you can do the exact same thing with a flame test. You set a sample of matter on fire, and the heat, the energy, the activation energy coming from heating it up causes the electron to jump up in energy state, fall back down, and give off energy. Someone had a hand up still. Will, you had a hand. Yeah, those were the main supporting evidence he had. Yeah. Yeah. I would say that like his model though is still not the model we currently use. Right? We've actually tomorrow's lesson is going to be on the quantum model, and it's even more confusing than this one is. So, okay, I need to get going here because I want to get you guys some time to work on your test. What basically happened then is he was able to create these emission spectrums where you had just these few lines showing up right here as electrons were basically bumping up and coming back down, up and down, up and down, and on the releasing side it was giving off energy. And it's also possible to have what's known as an absorption spectrum. An absorption spectrum is the opposite way. What you do there is you shoot white light. White light is all of the colors, by the way, right? So shoot all of the colors at a gas. Okay. And then what it's going to do is it's going to absorb only the frequencies needed to move electrons from this level to this one. So basically, in an absorption spectrum, you shoot every single color, not one color, but shoot all the colors of light at a sample, and then this one is missing. This one is missing. This one is missing. Why are those ones missing? Well, those were the energies required to make the electron go from levels 1 to 2, or from 1 to 3, or from 1 to 4. Right? And as they fell back from 4 to 1, or 3 to 1, or 2 to 1, you would re-get that color back again. Yeah. It would just make it seem like you'd see it better, but like the intensity of light would not change where these color bands would be. Does that make sense? Yeah, because as we've learned in quantum theory stuff, intensity actually doesn't really make much difference at all. That being said, if you had a really weak light, you wouldn't see it all that well, right? So the more intensity, the better it would show up. Okay. So these then are known as spectra. If you guys were able to see it today in my quick little demo, that's fantastic. If not, like I said, I want to spend time doing this on Friday, and hopefully you get the concept. Mercury right here, this is an electron going up and back. An electron going up and back. And sometimes they can go from not just levels 1 to 2 or 1 to 3, 1 to 4, but they can also hop from levels 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5. So that's why you can get a whole bunch of different lines here. What I need to show you guys how to do today then basically is a couple of quick math calculations for any questions that you'd get math-wise on this. But for the most part, this topic is entirely theory-based. Yes? Please focus. Okay. So I want to show you how to do a question that was determined by a guy named Rydberg. And he figured out a formula that worked for calculating just how much frequency these bands of light had. And he did it only for hydrogen. Now, I need to let you guys know, this is not on the diploma. So don't memorize this and be like, oh, we got to know this. But I just want to show you an example calculation before I show you the ones that we actually have to do on the diploma. Okay. This was Rydberg's formula. He figured out that if you wanted to know the wavelength of light being given off, you had to know a constant for the sample, which he calculated here, and you had to know which energy levels things were transferring between. So if it was going from a level 4 to 1, or 3 to 1, or 2 to 1, you just had to know which energy levels there were, and you could calculate what color of light you were going to get. So I want to try a question, even though this is not something you need to do. Hopefully it helps consolidate the idea. So I want to hop up to this example right here. Let's calculate the energy of an electron in the 4th energy level of hydrogen. Well, really, there's lots of energy levels, right? There's the first level that has 2 electrons, the second one that has 8 electrons. Does hydrogen use them all, though? No. So maybe if that wasn't clear, energy levels exist even if they're not being used by electrons. Like hydrogen has 1 electron. Right? But that 1 electron might not be in the first level. It could actually get bumped up to the second level where there currently are no electrons. It could even get bumped up to the 3rd level where there aren't any electrons. Does that make sense from a chemistry point of view? Okay. The noble gases, by the way, the reason why we call them the noble gases is because each energy level was full. So like helium is 2 out of 2. And what's next? Neon? Neon is 8 out of 8. Right? That's why the noble gases are considered noble, is that their energy levels were considered filled up. Good point. That's actually the reason why they get booted right back again, right? So even though an electron tries to go from here to here, it's going to get kicked right back again, and that's why light is given off. Right? So it goes teleport, right back again, give back the energy in the form of light. Yeah. Same thing as the noble gas ones, though, right? The electron doesn't really belong in the energy level it got moved to. So the kinetic energy of the electron kicks the electron to a new level, right? But that's not where it belongs, so it tries to return right back home again. But in doing so, conservation of energy would dictate that if you received energy to get there, you can't just go back again, because otherwise you'd have too much energy. So it has to lose that energy again in the form of light. Right? So really it doesn't really matter what element we're talking about. As soon as the electron gets excited to a higher energy level, it wants to come right back again, is the idea. You know what? Let's skip this question here. Let me go to this one right here. Can I show you guys this picture here? I think this might help with your understanding with where we're at, and I'll loop back again. Here's kind of a diagram that we might have that kind of diagrams how energy levels could exist. This one right here is the lowest energy level we have, and we have a name for it. We call it the ground level, okay, which is basically the first energy level. It gets bumped up to level 2, or to level 3, or to level 4. But really, the bumping this thing up to a higher energy level, we don't care about that so much. We care more about when it returns. Okay? And an electron got lost. It's no longer in the place it's supposed to be. It has to come back to its home again. And in doing so, it could go from 2 to 1, from 3 to 1, from 3 to 2, from 4 to 3, 4 to 2, or 4 to 1. And each one of these lines right here corresponds with one of these color bands that you're seeing there. So the question then is, can we calculate that color? So which one was I on? I was on this one right here. So it said determine the energy change and the wavelength of EMR as an electron drops from N2 to N1. In order to solve a question like this, you're going to have to be told what the energy level was on N3 and N1. Like, I would have to tell you what those numbers are. So I believe this question right here, I left it just to be like making up numbers. So as an example, why don't we say this is, say, like 1.67. Oh, goodness, Chris. I can't write today. My pen is not working. Let's make up some numbers. 1.67 electron volts. And then this number right here might be 2.13 electron volts. And this number might be 4.23 electron volts. And this number here could be 6.17 electron volts. You will be told these numbers. You have to be. Okay. Well, if you want to figure out the wavelength of light emitted, all you've got to do is figure out, well, how much energy was lost as it transferred between the two energy levels. So how much difference is there between 4.23 and 1.67? Just subtract those numbers. So 4.23 minus 1.67. Again, those were made up numbers, by the way. I just randomly made up some numbers here. I calculated a difference in energy of 2.56 electron volts. So what does that mean? It means that something caused an electron to go to a location it's not supposed to be. The electron was supposed to be here. It got bumped to a higher level. And then immediately, it went right back to where it was supposed to be. But in doing so, it re-emitted energy so that energy is not lost in the form of light. We can then take this amount of energy and use the formula E equals hc over lambda, and we can solve for the wavelength of light we expect to see. So this was 2.56 electron volts. This will be 4.14 e minus 15. This one will be 3 times e to the 8, and I should be able to solve for the lambda. The reason why I picked the 4.14 number, by the way, is that the energy value that I gave you was also measured in electron volts, so I just made sure to use the same number. So let me do a quick calculation. 4.14 times 10 to the minus 15. I'm going to multiply it by 3 times 10 to the 8 and divide by the difference in energy. And I calculated with my made-up numbers again. I calculated 4.85. E minus 7. In terms of wavelength, then, that is 485 nanometers. What color of light would that show up as? Blue-ish, blue-purple, yeah, probably in the blue-purple range. Which is why, again, in these pictures, you might end up with, over here, some purple light, because that was dropping from 3 down to 1. So what I need you guys to know is that you're not going to be asked to calculate what these values are right here. They'll be given to you. Okay. The slides I'm going to skip over, I think, due to time, is that Rydberg actually calculated a way to calculate the energy levels, but only for hydrogen. And we don't use this formula, so maybe I'll just skip this because I'm taking up all your time today here. And this is another formula that Bohr discovered as well. And again, we don't even use this formula either. So why don't I, in the interest of time, skip that. But the idea is that you should be able to tell you basically what these energy level diagrams are. So let me finish with one last slide and then I'll call it a day here. This slide right here. We should actually be able to tell you where this wavelength came from. This would be an example of a picture you might get. I know that n being 4, n being 3, n being 2, and n being 1. This diagram has kind of told me all of the energy levels. Right? And so if an electron drops from energy level 4 down to level 3, it says it's going to give off this many nanometers. Right? Let's just do a quick calculation to confirm. So 4.14 minus 1.96, the difference in energy between those two levels, I got 2.21 electron volts difference. That is the change in energy causing it to go from this state back down to this state. Well, that should be equal to hc over lambda. So again, c was the speed of light. H, I'll use the 4.14 number. And let's just calculate to see whether we get the exact same number they did here. Hopefully we do. So 4.14 e minus 15 times by 3 e to the 8 divided by 2.21. And I ended up getting, well, actually when I did this calculation here, of course it's just slightly out. I got 562 nanometers. Anybody else get 562 as well? Yeah. So, I'm actually not sure why there's a discrepancy between the two in this diagram. It's probably this number right here has more digits than 4.1. It's 4.14, right? Okay. It probably used a bigger number there, or they used the speed of light technically as 2.996 e to the 8 because that rounds as well. But that's basically all I need you guys to know in this unit here is the theory behind the new Bohr model. The idea that electrons are actually teleporting from one level to the next, and when they get teleported up a level, they've gained energy. They shouldn't be there, so they fall back to the previous level, and in doing so, they have to give back their energy. But they received their energy in the form of kinetic energy. They can't give it back in that form anymore, because they're teleporting, right? So instead, they give it back in the form of light. And this is where I'll end here. Have you guys seen the Northern Lights before? The Northern Lights are the classic example of basically Bohr's model of the atom. Okay? Here's my notes on this. Earth has a magnetic field, and there are electrons trapped in Earth's magnetic field. And those electrons just happen to bump into oxygen and nitrogen, because isn't our atmosphere just filled with oxygen and nitrogen? And so if the conditions are just right, free electrons run into other electrons, cause those electrons to get, the word we use is excited. That's the phrasing we use. Electrons get excited and they go from a ground state to a higher state where they don't belong. So when they come back down again, they emit a color. And the Northern Lights emit this color here, which is a really green color. Yeah. Yeah. The energy, yeah. that's the thing. They're not physically moving through the matter anymore, right? Well, because they gained energy in order to go from here to here, right? In order for them to go from this location to this location here, they had to have gained energy, right? And they gained it from this voltage supply, or they gained it from an electron hitting it, right? Something caused this electron to become exciting, gaining energy, right? But rather than a typical momentum question, right, where if I were to, you know, take these two objects and throw this one at that one, right, it moved through the air, right? Well, what it's suggesting is it gained energy, but it didn't move in the traditional way of moving. It literally, it jumped from one spot to the other, right? So in doing so, now it has more energy than it's supposed to, right? So we've now learned a new way that you can. Now we've learned a new way that you can release the wavelength, basically. Yeah. So this is a second way that this can occur, right? So wavelengths can be released as electrons move from here to here. But yeah, I would disagree though. It's not accelerating because it's not actually moving through the medium anymore. Okay. Can I give one last thought, and then I'll be quiet and I'll answer your questions individually. This is such a strange concept that the questions you guys have are logically the questions that scientists at the time had. And there's flaws to this model, because we've now since learned that like electrons don't behave as matter, they behave as waves. Tomorrow I want to talk more about the idea of superposition. The idea that electrons basically, they don't exist in one spot. They exist everywhere at once, simultaneously. And it isn't until we look for them that they actually finally choose a place to be. And that is such another weird concept. Can I say that one more time, then I'll stop? Bohr's model is still wrong, because Bohr's model presumes that electrons are always in one spot or another. It's either here or it's there. And the new quantum model of the atom suggests that if I ask you where is the electron, you would say it is everywhere until you look for it. And as soon as you try to find where it is, now it's either going to be here or there or there. But before you looked for it, the electron was literally at all places at all times. And that's why Schrodinger had such a crazy analogy of a cat that was both alive and dead, because it was actually able to be in a superposition with itself. Okay. So why don't I stop my lesson here, because I've accomplished what I needed to. If you guys want to take the next half hour or so to keep writing your test, you can. And if you have questions, why don't I answer those like one-on-one now? Does that work?